Welcome. Let's solve Leetcode 1462 course schedule 4. Okay, let's make this bigger so we can read it. So we're given a total number of courses you have to take labeled from 0 to num courses minus 1. You're given an array prerequisites where prerequisites I equals AI BI indicates that you must take course AI first if you want to take course BI. For example, the pair 0, 1 indicates that you must take course 0 before you can take course 1. Prerequisites can also be indirect. If course A is a prerequisite of course B and course B is a prerequisite of course C, then course A is a prerequisite of course C. You are also given an array queries where queries j equals uj vj, where the jth query for the jth query you should answer whether course uj is a prerequisite of course vj or not. Return a Boolean array answer where answer j is the answer to the jth query. Okay, fair enough. So in this first example, we're given two courses, and the prerequisites are given as 1 comes before 0, as indicated by the graph or this image here. And the queries say, the first query says, must 0 come before 1? And according to what they've given us, no, that's false. So that's why the first output is false. And then the second query says, is 1 required to come before node 0? And that aligns with this prerequisite list they gave us. Okay, moving on, let's go to, maybe let's just jump to example 3. So they give us 3 nodes or courses and prerequisites. So node 1 comes before node 2 as indicated by the graph, 1 before 0 as indicated by the graph, and 2 before 0 also indicated more specifically by the arrow. So then they ask us, does 1 is 1 a dependent, or must course 1 be completed before course 0? And yes, it is. So that's why there's a true. And then they ask, must course 1 be completed before course 2? And yes, it is. So both values are true for the output. Okay, let's get started. I don't think it's too difficult as far as the understanding of the problem description. All right, so let's get started here. So our approach will be something along the lines of maybe topological sorting, or maybe even like depth first search exploration. So our approach will be this. We'll well, for the graph, first we'll start with the I guess the edges. What did they give us? These prerequisites. So we will loop through the prerequisites and prerequisites and create a graph. So the graph will be for us to utilize during it will help us for furthering our solution. So once we have this graph from the prerequisites that they gave us, what we'll do next is, we'll actually do a little bit of somewhat of a, what's the word? I'm going to call it a lazy search for solutions. So by that, what do I mean by that? So when we loop, or let me see, when we not loop, loop is okay, but when we examine um, each query, only at that point will we find that solution. Find that solution. So, for example, so when we have this query here 1 0, what we'll do is we'll at that point we'll start exploring the graph to determine um, which nodes are dependents of 1. Okay, so let me see. So let's write that down. So at this point, we will determine which nodes are dependent of the query node, And lastly, what we'll do is we'll cache our results. So this is what I mean by that. So suppose we have let's do something here. Let's make a new test case. So I'm going to make a new test case. And my test case is going to be, we're going to have maybe 6 nodes. And the first node or prerequisite will be from course 0 to course 1. And then we'll go from, hopefully let's make this bigger so you can see it. We'll go from course 1 to course 2, course 2 to course 3, course 3 to course 4, course 4 to course 5, and lastly course 5 to course 6. We probably didn't need as many nodes, but it's fine. And the queries we'll just do, okay, 0 to 1, and then maybe we'll just maybe do one more, maybe 2 to 5. How about that? Or 2 to 6. Let's do something here. Let's do first 0 to 6. Okay, so this first query, well, sorry, let's go first over this. So this prerequisites. So let's examine what that looks like. So that means our example would look something like this. So this is our example. And in the queries, I'm asking 3 queries. I'm asking, does 0 come before node 6? Let's just verify that. So does queries come before node 6? And then I'm asking, does course 1 come before course 0? And lastly, course 2 before course 6. I'm asking each of these 3. So the approach that I'm telling you is this, or recommending is this. So let's look at this first query here. So what we'll do is we'll say, okay, oh, maybe not 1. Well, sorry, I missed a node, maybe. Actually, is there a mistake here? So 0 to 6, that means so there's 7 courses. I apologize. Yeah, okay. Okay, so when we first explore 0 to 6, this is part of the problem where I said we examine each query and only at that point will we find the solution. So once we have this query here, we'll explore 0 all the way as far as it can go. And then we'll save it. So then what will happen is we'll have this. We'll say like node 0 is a dependent of 1, 2, 3, 4, 5, and 6. That's what will happen. We'll save this. But while we're doing this, like imagine this wasn't there. So in essence, we would get something like this. 1 would be a dependent of 2, 3, 4, 5, 6. So hopefully you kind of see what's going on. And let me just do one more. So while we're exploring to the very end, we'll notice that, well, couldn't we also take take off 1, and meaning from the code's point of view, it doesn't know where it's starting with. So because we'll use recursion, and every time we'll pass in a new node, and every time we pass in a new node, we'll store it. So for this next recursive call, as far as the function is concerned, it'll say, okay, I am a dependent of these other nodes. And why is it helpful? Well, it's helpful because, so even though we find the solution for this query, notice how later on we can utilize what the work that we've done for this query. And so that's the trick, or not the trick, but what we'll be using to make our solution efficient. Okay, so let's kind of get started. I may refer back to this example as we go along with our implementation, or continue on with our implementation. So I'm going to change num courses to N. I'm going to change prerequisites to P, queries to Q, and that's it. Okay, so let's create our graph so that'll help us, assist us as we find our solutions. So we can say G equals a default dict, and we'll just make it a list for now. Then we'll say for U, V in prerequisites, and then we'll say G of U dot append pen V. And let's just print it out just so we can get a visual. So we'll say for key V in G dot items, and print okay, and then we'll return something. What do we need to return? We'll just say false times the length of queries. Okay. Is not of type integer. Oh, I must have made a mistake during our test case. Oh, I didn't close it here. Okay, so let's go over maybe this example here. So we're given these prerequisites, and I wanted us to see the graph. So as far as the graph is concerned, currently it says node 0 is a prerequisite of node 1, and 1 is a prerequisite of node 2, and then so on and so forth, which aligns with our original depiction of the graph. So this was our original depiction. Okay, so that's fine. Okay, great. Now, what would be helpful is if we had something like this. So you know how it says 0 is a prerequisite of 1? It would be better, or for our situation, if it said, because even though 1 is a prerequisite of 2, 0 is also a prerequisite of 1 and 2. So I think I already explained it earlier, but I'll say it again. It would be better if we had something like this, where we have this node, and then it knows all the, like, what's the word? Indirect dependencies, or all the indirect prerequisites. So even though 0 is a direct prerequisite of 1, 0 is also a indirect prerequisite of course 6. So that's what we'll be doing next. So let's do that. So we'll make a function that will do that for us. So we'll say, okay, we'll say we'll have a function here. I can't think of a good name, so I'll just call it f, and we'll pass in a node. So imagine we're passing in this node 0, and we want to go all the way to the very end and eventually have this type of thing, or this type of data structure. Okay, so let's do that. We'll say, okay, so originally we'll just add that node to our prerequisites, and then we'll say L. So give me a moment while I type this out, and I'll explain what we have. Okay, so what we're going to do is we're going to explore um, our dependencies using L. So L will be the list of nodes that we're starting with. V will be, well, let's write this down. So V would be the visited nodes, or the visited, but also there'll be the visited nodes, but also the maybe the dependency nodes, dependency nodes, and then this will be the nodes to explore. Okay, so originally we'll start off with this node that that's passed in. Okay, so then let's begin. So while we have nodes in our our list here, it doesn't matter, and then we'll pop it out. We'll say, okay, u equals l.pop. It doesn't matter in what order we traverse it. We just want to explore it till we've exhausted all edges. And then we'll say, okay, for v, so this is basically a neighbor in g of u. So at this point, we're exploring all the neighbors of the current node. I could have easily done something like neighbor here, but let's just keep it like this. Then we'll say, okay, if we haven't visited this node yet, so we'll say if this node has not been visited, so we'll say v not in v. Okay, so then we say, okay, if we haven't visited yet, now we're going to visit you. We're going to say, okay, v.update. So what are we going to update? So v is currently a set. So what we'll want to do is we want to add more elements to this set, because remember, the goal is to end up with this. So imagine we pass in node 0, and then we're here, and node 1 is a neighbor of node 0. And imagine this is our first time entering this function, so 1 would not be in v, and that means we want to explore 1 to the very end. So whatever nodes are dependents of 1 will also be a dependence of 0. So and the same thing for node 2. The nodes that are dependents of 2 will also be the dependents of 1 and 0. So my point to you is this: we'll want to incorporate or include the dependencies of our neighbor as well. So how do we do that? So let's say we'll call our function, but with the neighbor, but then we'll include those indirect prerequisites into our prerequisites. So let me just make a comment there. Include indirect prerequisites. Prerequisites. Okay, so that's what's going on here. So we explore our neighbor, and then our neighbor, whatever our neighbor is a prerequisite of, we're going to add that to us, because that just makes us an indirect prerequisite. I hope that makes sense. Okay. And then once we're done with that, we can just return v, and v is our even though it's also like at some point it's like a visited set, but it's also like a list of dependency nodes, or it's also the indirect and direct prerequisites. Okay, so let's leave that as it is, and then now we can loop through our queries to figure out what's going on. So imagine this now. So this function, what does it do? This returns the prerequisites. Sorry, the dependencies. Of node. Okay, so now we're going to say, okay, so when we loop through our query here. So when we say, okay, so for, well, let's just make this easier for now. So for u, v in query. So the question is, what's the question? They want to know, you should answer whether the course u is a prerequisite of course v or not. So they want to know if v is in f of u. So remember, that's what this returns. It returns all the dependencies. So they want to know, is v a either a direct or indirect dependency of u. Okay, so then that's what we'll have, and we'll just make an array out of this. So we'll say, okay, we'll make an array out of this, and then we'll just return it. Okay, now let me just test it. And we're not exactly done yet. Okay, what do we have here? Oh, my apologies. So we're not exactly done yet. So I'm actually gonna submit it, and we're gonna have an issue. I'm doing this on purpose for educational purposes. Now think why we'll be having an issue. So the first indicator is, well, it's taken a rather long time. So we have a time limit exceeded. Okay, great, no problem. Now, remember what's happening here is, I kind of hinted at it earlier, is that suppose we're solving this answer, 0 to 6, but indirectly, at some point, we had to solve, for example, we had to loop through it, and then imagine at some point this was node 0, but then it moved on to node 1, and then it moved on to node 2. So my point is, we know all of these answers. We know from all the way down to 3, and then all the way down to 4. We know all of we know all the dependencies of these other nodes because they were required for us to find out the result for this one. So my point to you is this: we should save that, and we can save it by using this this caching. Let's just use that here. This caching decorator. So we'll use that, and then what will happen now is that our work will be preserved so that when we use a query that's similar to the work that we've done, our answer is used again. So we don't have to do double the work. Okay, great. So it looks like our solution is very good. Looks like it's very fast. In fact, it's faster than every other result apparently. So high five. Okay, great. So if you have any questions, please leave them in the comments, and I'll address them as best that I can. If you found this video helpful or educational or beneficial, please consider liking or subscribing, or both. Other than that, have a wonderful day. Take care of yourself. Cheers.